Good day. So we're going to do a several number of problems here for Chapter 5, Rigid Body Equilibrium. So for our first problem, what do we have? We have a landing gear. So this is a landing gear connected to a wheel on a plane. So the plane has come down, and we have a force of 6 kilonewtons coming up through. That would go right up to this the hub right here. And so as the plane is coming down like this, the force here at the axle is 2 kilonewtons to the right as well. So there's the impact this way and impact that way, shall we say. All right, so we have, this is the forces from the tarmac going up into the wheel. We have X and here's Y, the usual coordinate system. And so on this plane we have this main strut that's coming down. All right, and so this is at 20 degrees to the vertical. Here's A, where another strut comes down. And so these have, there's 30 degrees between them. And then up here, they pin connect into the fuselage of the airplane. All right, we have a little geometry. So here's 20 degrees, 30 degrees. And this point A is 0.6 meters up. And where it connects into the fuselage is a 0.4 meters above that. So relative to the axle, these points are 1 meter above. And then we don't know what the radius of the tire is. We don't need it. So for this problem, we want to find the reactions at C, so where it's pinned in. And the other thing we want to get is FAB. So there's going to be a force along this member. Now, what can we say about this member? This is a two-force member. All right? We don't know anything about the mass, so it's massless. We don't have to worry about that. And so you'd have forces at a force at the top, which would be in the XY plane, and the force at the bottom in the XY plane. We know that if this plane is not crashing, that this is stable. All right? So given that this is in a stable condition, that says we have a two-force member, and that means when you have a two-force member, the forces have to be equal, opposite, parallel, collinear. Let me put that into other terms. The force is moving on a line between the connections. All right? So between connection A and connection B, the force is on a line. So what that means is that even if this strut, for some bizarre reason, if they constructed it with a bow, all right? So I'm just putting really lightly this thing out here. The force goes on a line between the connections. It doesn't go walking along this whole unit. It's on a line between the connections. I'll take that out. All right. So that finishes up the comments I wanted to make about a two-force member. All right. So now, here's this member here. So there's a force at C, there's a force at A, and a force here at O. Guess what? This here, OAC, is a three-force member. If we want it, so at the end of the day, so here's what's happening at the axle. We could express that as a vector. So up 6 over 2 would be force kind of along this line. We're going to figure out what this is, and then knowing what that is. So here's something we could do. If we actually plotted this as a vector, up 6 over 2, all right, so we'd have a line going up like so, and then wherever that connects, well, then we could actually go right here and draw a line, and that would tell us the line that the force in C is acting on, because we know that's stable, where it's in static equilibrium. And then we could use that information and solve it. That would take a lot of graphics for me to set that up. So we're going to use the fact this is a two-force member to put this force on this line. All right. But we're going to solve the rest of it conventionally using just algebra. All right. So let's do that. But you could graphically use the three-force member and solve this problem. So now, let's take care of some geometry. So we know from here to A, well, this is 1 meter. How long is from O to C? And I'd like to find out how long is from A to C. So let's make that happen. So I know O to C, cosine of 20 degrees, or this is 70 here, so I could take the sine of 70, whichever one works for you. I'll write sine of 70 equals 1 meter. All right? That's true. So there's 1 meter, and let's go to a pen which is darker. If I solve for OC, that would give me 1.0642 meters. So that's how long that is. Now, how long is this piece? Well, if this is 1 meter and this is 0.4 meters, the vertical from C to A, it says that from A to C, this is 40% of that. All right, so CA equals 0.4 OC, which is simply 0.4257 meters. So now I have some geometry, some distances and things I can work with. And we've already noted AB is a two-force member. All right, so let's solve this thing. So if I go and look at what I have here, okay, that's known, so that's great. I don't know what this is. I don't know what that is. So I have too many unknowns. 1, 2, 3. All right. Relative to this force, I don't know magnitude, but I do know direction. I know exactly the orientation. So I have 3 unknowns. I need to get rid of some stuff. So here's what I'm going to propose to do. I'm going to take the moments right here up at C. All right. If I do that, then I have, that wipes these out, and so then I can solve for FAB. Then once I have FAB, if I sum the forces in the X and the Y, I get everything else. Bam, done. This is standard protocol. Form your free body diagram, and very often the first step is take a moment at some convenient place to wipe out a bunch of unknowns, solve, and get an answer. So that's what we're going to do. So let's see. We're going to sum the moments at C, which seems like a very logical thing to do. So if we look at what we have here, we have 6 kilonewtons, and if we follow that up, we would need this horizontal distance to go with it. So as 6 comes up, that's going clockwise, so we'll go a -6, and then I need to have this distance. So I know this here is 1.064, all right, and then I can simply take, if I go here, take the cosine of 70 degrees, I would have it. So 1.064 cos 70. Or I could take sine of 20. Both work. All right, then I have 2 kilonewtons, and this distance, perpendicular distance up, is 1. That's going counterclockwise, so plus 2 kilonewtons times 1 meter, out. Now, got to deal with FAB, and we could be really slick in doing this thing. All right, I could use this 40 degrees here and break it into an X times this distance and a Y component going down times that distance there. That's too hard. I want to do things as easy as possible. So let's look here. You see this thing I got? Here's this coming down. Here's 30 degrees. If I were to take this force, sine 30 degrees, okay, I would get a component of force going this way. Can you see what I'm doing? So here's sine of 30 degrees. It would come in at a right angle here. Now we would need to envision this force actually happening this way. But this is at 90 degrees to AC. This is 30 degrees off of there. So I'll just take the sine of 30 times FAB. That would give this force. And I know exactly, see what I did here? See it? I know this distance. The perpendicular distance is that. Now by doing that, if I took the cosine, that would be a force along this line, which is lined up with point C. So it does this component of the force here can't have a moment. It's lined up. So that gets rid of a bunch of stuff. So watch this. So if this FAB was here, the component, anyway, don't have a good name for that, but anyway. So I'll take the 30 degree sine component, whatever. So if this is coming in here, that will be going around, that's clockwise. So I have a negative. All right. FAB sine 30. There's the force component. And then this distance here is CA. And we know that is 0.4257. And sum that all equal to 0. So solve for FAB, get 0.864 kilonewtons. We're all set. Now, so we'll just bring this up here. Now that we've done that, so we know FAB, we got a positive here, so our assumption that that was pushing down was good. All right, so now we just have to sum in the x and the y, and we'll get all the rest of the answers. So summing the forces in the x, set that equal to 0. There's 2 kilonewtons to the right, that's positive. Then I have FAB, I'll take cosine of 40. That'll go in the other direction, minus FAB cos 40. And then I have CX going in the negative direction, so minus CX, set it equal to 0. And solve... oops. Actually, I forgot something here. Forgive me. This is a minus when you do this. So I assumed the force was going in this way. It's actually going the other way. That makes... So whenever you assume a direction, if you get a change in sign, there's no disgrace in it. You just, oh, force is going the other way. And I just don't have good light in the room at the moment where I'm doing this, and I couldn't see the negative sign in my notes. So sorry about that. That's negative. Please note that. All right. So since that's going the other way, that makes that positive. No problem. Solve for CX. Get 2.662 kilonewtons. Now, summing forces in the y. Set it equal to 0. I have 6 kilonewtons coming up. I know I got that right. This we now know is going up. So we have plus FAB sine 40. And I had CY going down, so I'll subtract that off. Set it equal to 0. Solve for CY. And we would come up with 6.555 kilonewtons. And there we go. This problem is settled. I will reset here, and I will see you again in a moment.